Today I'll be presenting on Stateful CDC. So for this, like to fully explain how it works, I had to do like an end-to-end explanation, starting from the source of where the data comes from. But from a high level, Stateful CDC allows you to get your real-time updates for your Venice store locally in your application. And it also persists its state upon restart. So the source of everything is like when you're doing your real-time writes. Okay, so like the source of everything is the online producer. So
go ahead.
Okay. So the online producer is one of our applications that can use to write to Venice Store, and the Venice Store has to be hybrid. And this could be writing in like a Samza or a Flink job. And the online producer is going to be writing directly into the Venice real-time topic, or also known as the RT. And once it's written into the RT, how far can it go to the right? Okay. Then we have the server, who's the leader. Is going to be consuming the RT, and it's going to be writing it back into the version topic. Yeah, VT. So like an example, this would be like version 1, and this would be the topic. And then once it consumes the events from the RT, it's writing it into the VT. Now, once it's in the VT, this is the topic that's going to be consumed by the server followers. And this is where CDC comes into the picture. So your CDC client. Yeah, it's going to be reading directly from the version topic. And when that event is consumed from the version topic, the client is essentially polling. And for CDC, it is essentially a wrapper built on top of a DaVinci client. And on top of DaVinci, we actually have another abstraction on top of it called DaVinci Record Transformer. Also known as DVRT, if you heard that phrase thrown around many times. So this is like an abstraction that allows you to control like the life cycle of your DaVinci application and what you want to do with it. So previously DaVinci, like it only writes into its local cache, and you give it a key that you want to query out of. What DVRT does is it kind of sends you like a push notification when you receive a new event. And what we do here with Stateful CDC is that when these events happen, we are first writing it into an in-memory buffer. When the user, for example, the user app, they will be pulling from this in-memory buffer, and that's when they're getting these events. And additionally, like we're also, after we're writing into the in-memory buffer, we're also writing into, is this still in? Okay. RocksDB. So what happens inside the user app after they're pulling for these events? They can decide to do whatever they want with it. If they want to transform it, store it anywhere else. Upcoming use case is semantic job search. So what they want to do is like they're writing vector embeddings of job postings to Venice. And on the client side, they want to consume those embeddings and store it inside directly in the GPU. Once it's inside the GPU and a user query comes in, for example, like a LinkedIn user wants to do like, hey, I want to find a job for software engineers. So this will get converted into a vector embedding. And then this request will be sent into where the GPU nodes are. And once that happens inside the GPU, which has like an in-memory hash map of the data, they're performing like a vector similarity search. Basically performing like a top K, hey, what job postings are most relevant based on what the user queried. And then once that happens, the relevant job postings are returned back to the user.
Quick question. So is the CDC client sit on the user app or it's a separate like nearline job?
Yeah, so the CDC client is directly within the user app. So yeah, so it's like how it goes like user application. They have their own logic here. Then they spin up the CDC client, and then that's when they're consuming it into example like into their GPU.
Got it.
And what makes this different from the stateless CDC client is that we're writing everything into our local RocksDB file. So when the application is restarting on the deployment, what happens is that first, it'll scan every record within RocksDB and load it into the in-memory buffer. And when the user pulls, they'll be getting those on-disk records. And that basically gives them a compacted view of their data. And another thing too, like when we're consuming from the Kafka version topic, we're persisting all of our checkpoints on disk into something known as the offset record. So this allows us to maintain like, hey, when you restart, you don't need to resume from the beginning of the topic, which is what the stateless client does today. And the reason why this is so important is that for, yeah, go ahead. Oh. Okay. So the reason why this is so important is that for the online producer side, the users are sending a lot of duplicate keys. Like for example, like ads infra, they're updating the same key like multiple times a minute. And that can lead to an explosion of the version topic. So when in a stateless client, when you try to consume from the beginning of the topic, that can make their bootstrapping time like bad. And the way we deal with this today is a combination of the stateful client plus
I'm sorry.
okay. The stateless client, sorry, stateful client plus topic compaction within Kafka. However, topic compaction will not be supported in Northgard. And the way we're going to be dealing with that is through blob transfer. And how it works is like you have multiple instances of your stateful CDC client, for example, over here. So like this is an existing one right here. And you have a new one that's coming up. And there's nothing on disk. So what it does is it does a search for its local peers and hey, it found this client. And it has RocksDB data. So what it will do is that it'll take a snapshot of this information and send it directly to the client. So it'll have its RocksDB data too. So basically this kind of like prevents a cold start having to resume from the beginning of the topic, and it'll instead resume from the last checkpoint within that was stored on this node. And that makes restart a lot quicker. And The reason why, like we also have our own solution for like topic compaction, which we call log compaction. That's directly from the controller. However, all of our like many of our CDC customers rely on 1 hour compaction intervals, and the Venice push job, which is how we're implementing compaction, only has a 24-hour SLA, which is way too slow for the 1 hour compaction that they depend upon. So a combination of stateful CDC plus block transfer addresses this issue. But on the server side, like this isn't really big of a problem because the data is partitioned and it's spread across a fleet of like 200 nodes. So it can tolerate all this duplicate data. But usually for our clients, they're subscribing to every partition. And that's where we see issues. So what, for example, when I was first ramping Ads Infra and we were trying the stateful client, we created a version topic that had a default compaction interval of 24 hours. And when it tried to consume from the beginning of the topic, it would take several hours to bootstrap. And that was completely unacceptable for them. So I turned on the 1 hour compaction interval, and that brought down from several hours to, I think it was like 4 minutes from remote consumption. Any questions so far?
So question regarding the block transfer and the bootstrap. Instead of consuming from the version topic, they could do a blob transfer from the server to the RocksDB instance.
So it is technically possible that a DaVinci client could do a blob transfer from the server, but that's not supported today. I'm not sure if that's in the roadmap, but I think it's definitely possible.
And let's say there are multiple instances of like the application running. How does it know which instance to get the blob transfer from?
So probably Jolin or Jingyang can better answer that. But from my understanding is like when a CDC client is like they are sufficiently caught up like at the end of the version topic within like I guess our new use case like within the last 1 minute of data, what it'll do is it'll announce to what we call as a DaVinci push status store, the system store. So it'll update its information in the system store. Then when a new client is coming up, it's going to be querying this system store and see, hey, what are the available nodes? Then it just does a random selection and hopefully like it distributes it randomly or even enough based on random.
One more question, and this might be coming from some ignorance, but how's this different than DaVinci use case? Like how is stateful CDC different than?
Yeah. So for Ads Infra, they were initially like for some of their other use cases, they were directly using DaVinci. But the problem is that the key space is completely unknown to them. So if they want some of that data, they would have to periodically query every single key in RocksDB to see which keys have been updated. So they would have to like manually figure out, hey, this key is updated. And it would also require them like maintaining the key set locally all the time. And that kind of makes it like a lot of like maintenance burden on them. Because instead of like knowing when an update happens, you just have to hope you hit the right key.
So they're trying to reduce latency. Is that the thing? I mean, for any key, they can just go to RocksDB and get the latest value of it, right? Like, so holding it in memory, it makes me think they want to reduce latency, and that's why we have all of this. I mean, it's not.
Yeah, it's because they're holding all this data in memory so they can perform their like vector like cosine similarities as fast as possible. Because if you read it from RocksDB every time, there's going to be some latency. There is the RocksDB block cache. That could also address it. There's also the plain table, but because I think there's some specific logic that they have in like their in-memory object where it's better to do it on their side.